Science 8, it's Mr. Drzezinski. I have another video for another Simple Machines activity. This one's called Incline Plane. The instructions for the incline plane suggest you need these materials. I have a ramp here that I built. I'm going to use this for the incline plane. It asks you to get a spring scale that'll do newtons, which I have here. And then it asks for a block, but instead of a block, what I got here is a plastic bottle filled with rocks. Put a little handle there on the top. And then we're going to try to lift this up and lift it up the ramp. Step number 1 reads, attach the spring scale to the block. Lift the spring scale and block into the air and determine the force necessary to lift the block in newtons. Okay, let's see if I can bend you down a little bit for that. Okay, here's the weight. I'm going to attach this spring scale to the weight and let it measure the number of newtons. I'm reading that at 5 newtons. Next, step number 2, place the block at the bottom of the ramp. Use the spring scale attached. Start to pull the spring scale up the block. Determine the necessary force to move the block. Let's set this down at an angle right here. And take my spring scale and attach it. And start to pull up on the spring scale and see how much it takes before I get this to lift up the ramp. This is more like 2.6 newtons. Step number 3, how does the incline help with the work? The incline plane is a simple machine that's going to provide a mechanical advantage. Rather than lifting this thing straight up, we're able to lift it up the ramp with less force. Okay? I will continue with this activity with the blocks and the nail and the hammer next. I'm going to continue on to the section that says wedge. This is an example of using a wedge as a simple machine. The materials here include a nail, which I have a roofing nail. That's a 1 1/4 inch roofing nail. It asks for 2 boards. I have these 2 pieces of poplar. I think one is pine actually, but it says bottom on it, and this board says top on it. And they ask you to have a hammer, which I have this rock hammer. I found this is for chipping rocks, sort of a masonry hammer. It was already here at school. Step number 1, stack the 2 boards. Step number 2, lift the top board from the other. Is it connected? Currently, they're not connected. Step number 3, restack the boards. Step number 4, add the nail through the first board to the second board. I have a pre-drilled hole here where the nail is sitting through the first board, but right now it's hitting into the second board. When I hammer the nail in there, the nail is going to pierce the fibers of the second board and push those apart and embed itself down there. It will act like a wedge on the front. Step number 5, lift the top board. Are the boards connected? Now they are connected. Number 6, what force keeps the 2 boards together? This nail shaft is now buried into the second board, and the shaft is spreading out the wood fibers, and the wood fibers are pushing back onto the nail. And the tension between the wood fibers and the nail is keeping the nail into the bottom piece. The top piece is stuck to the bottom piece because of the head of the nail. The head has now pushed the top piece into the bottom piece. Where does the force come from? The force to hold this together came from my muscles and the mechanical movement of the head of the hammer to hold those two together. We run the Simple Machines activity, the part where it talks about a screw. I brought today with me the Pampered Chef apple peeler, corer, and slicer. This same device will peel the apple, take the core out, slice the apple. I have it mounted on the end of the table here, and I'd like to demonstrate it. It says in step number 1, mount the device at the end of the tabletop. I have it clamped here to the surface, and it'll crank here. Place a clean apple on one end. This is a quick release. The apple goes on these prongs, nice and tight. Step number 3, it says turn the handle to peel, core, and slice the apple. Okay, so here's the screw mechanism here, and as I turn the handle, the apple is feeding forward. Right in here, it's going to hit the peeler. When it hits out here, it's going to take the middle out. Okay, here's the peel. Here's the slices. And then here's the core. Okay, and then this device is going to make apple slices. Step number 5 asks, what did the screw do during this operation? The screw advanced the apple to go through the tooling to get peeled and cored and sliced. Name 3 other things that screws can be used for. They can be used for fastening, screws that hold boards together or metal together or plastic together. They can be used for feeding screws, like this does, or a vending machine. And screws can be used for pressing things together, like an apple press or a grape press. Advancing the screw can cause the apples to squish and the apple juice to roll out. The next section says pulleys. I don't have any pulleys here, but I have some pictures of pulley arrangements on your activity, and we can do these calculations based on these pictures. The first thing you'd like to know is the formula for mechanical advantage. This top formula suggests mechanical advantage is the force input divided by the force output. This is the amount of force a person's going to use. This is the amount of force that the object will be lifted. This mechanical advantage formula can be used also. This has to do with the distance the person pulls versus the distance that the object raises. That's distance input divided by distance output. So to do the first step, it says calculate the force Z necessary to lift a 100 Newton force with these 4 pulley systems. Step number 2, what is the mechanical advantage for system 1? System 1 is this big 1 over here. If you take a look at the H value, it suggests how high the load gets lifted off of the floor. That happens to be 10 centimeters. If you take a look at the S value, that's how far the person has to pull to get that to rise 10 centimeters. That S value is also 10 centimeters. Okay? And in step number 1, we would have 10 centimeters, which the person uses to pull, divided by 10 centimeters, which is how high the load raises. The 10 divided by the 10 equals 1. There's really no mechanical advantage on this first pulley. If you were to go over to try to pull, let's say 150 pounds, you'd have to be 150 pounds. It's a 1-to-1 ratio, which what they call a single fixed pulley. Number one is a single fixed pulley. The mechanical advantage is 1. As much weight as you want to lift is how much weight you have to pull. Not too much of an advantage there. Step number 3 says, what is the mechanical advantage for system 2? If you're looking at this arrangement, there's 2 pulleys, a single fixed pulley, and then there's a pulley with the load on it. If you look at the H value for that, it's suggesting that the load is lifting 10 centimeters. If you look at the S value, it suggests that a person's going to have to pull 20 centimeters. We can put the 20 centimeters on the numerator, the 10 centimeters on the denominator, divide 20 by 10, and you'll get 2. This pulley system has a mechanical advantage of 2. It'll make it easier for a person to pull that weight up. If you're trying to pull 150 pounds up, you might only need to give 75 pounds of force. Okay? What you're losing there is the distance. A person's going to have to pull on that rope twice as far as the object lifts from the ground. Step number 4, what's the mechanical advantage of system 3? System 3 has 3 pulleys. A fixed single pulley at the top, there's the pulley with the load, and then a third pulley, working in tandem. They're working together. If you take a look at the H value, it's lifting the weight, the load 10 centimeters from the floor. If you look at the S value, the person's pulling on there 30 centimeters. We could put the 30 centimeters here for the input. We could use 10 centimeters here for the output. 30 divided by 10 is 3. The mechanical advantage for this pulley happens to be 3. It makes it easier for the person to pull, but the person's going to have to pull farther to get less distance. The last step, number 5, what's the mechanical advantage for the system on number 4? Number 4 has 4 pulleys, the single fixed pulleys, plus 3 others in tandem. You can use the same formula. It shows the H value lifting the weight 10 centimeters. It shows the S value pulling the rope 40 centimeters. 40 centimeters is the input distance, 10 centimeters is the output distance. 40 divided by 10 is 4. The mechanical advantage here is 4. Much, much easier to pull on the rope, but you got to pull further to get the weight to come up. Mechanical advantage of pulleys. That's the best I can do in the activity. Let's go to the next thing. We're continuing through the simple machine activity. I'm on the section that is called wheel and axle. I don't have any materials for the wheel and axle. Step number 1, it asks you to sketch a wheel and axle and label the parts wheel and axle. You might want to get a picture online. You can copy and paste it into your activity. Anything that might have a crank on it here, connected to a shaft that's turning something over here. You have a bigger diameter connected to an axis with a smaller diameter. All those arrangements are considered wheel and axle, and there's a lot of them. When you see a person with a dolly, the wheel and axles on the dolly allow the dolly to move more easily. That gives a person a mechanical advantage with a dolly. Even a screwdriver works well. The screwdriver has a bigger diameter outside and a smaller diameter axle here to the point, which could be a Phillips or a slotted. But a person's able to turn this more easily with a bigger diameter out here. A wheel and axle also provides a mechanical advantage. Things like a doorknob on a door, if it's a round doorknob, when you grab there, actually the axle of the doorknob gets to be a smaller diameter to where the lock mechanism is. The bigger doorknob, rounded doorknob, provides you with mechanical advantage for opening the lock on the door. Ferris wheels, that well pulley that we saw in the notes where the rope is tied around the small axle that's lifting the bucket of water out of the well, and a windlass. A windlass, I think, might be that same idea, but windlasses are used on ships to crank maybe cables that allow sails out or in, or cables that allow the anchor to go down or back in. Those are all examples of wheel and axles. All right, so list them and get a picture. Thank you. We have the last unit on the Simple Machines activity. It's called hydraulic systems. Just finishing my apples. There's the apple slice. Short them out in round pieces. Here's the hydraulic jack. This is the handle. This is called the saddle and the ram. This is like the body and the handle. There's a release valve down here. And this is the piston right in here and the socket. The socket will hold the handle. Okay. And there is a plug back here where we can fill with more hydraulic fluid if we need to. Okay. There are some other things that come with it, including a stand here, which can be put on top of the hydraulic jack. This might be useful if you're jacking up the house and you need a 4-inch post or a 2x4 or a 4x4 that needs jacked up. This is rated as a 12-ton hydraulic jack. Here's how it'll work. On one end of the handle, you can loosen the release valve and allow you to push down on the jack. And then the release valve can be closed. And the handle used to pull the jack back up. Now there's a tremendous mechanical advantage occurring here. This thing would be able to lift 12 tons. This handle I'm using with very little force. There are two pistons. This piston, which is driving oil down, across to this piston, which is pushing the jack up. And this thing can be advanced like 2 or 3 inches, I would say. And you could lift cars, you could lift houses, parts of houses up with that device right there. Okay? If someone was to stand on there, we could easily move them up. This is another tool that provides a mechanical advantage, and a very significant one, using pressurized oil that's pushed from one cylinder smaller to another cylinder bigger. We're losing some distance, which means I have to pump this thing 3-4 times for this jack to just come up 1/8 of an inch or so. Okay, hydraulic jack.